Hello, my name is Charles Cook. Welcome to my first video on the QVFEM, which stands for the Quantized Velocity Finite Element Method. Today, we are going to set up a 1D shock tube code. So this will apply to the solid shock tube, the lax, the double blast wave problem. Okay, so benchmark problems involving, a 1D shock tube. Okay. All right. So I'll be writing today's code in MATLAB. All right. So I've set up my working folder and I'll be writing the code in Microsoft Visual Studio Code. You can use whatever code editor you would like. Okay. So I like to start all my codes in the same manner, which is clear, close all clear. So that's just gonna clear out the workspace, close all figures, right? Clear out the command window. Uh, so again, we're going to set up the 1D shock tube problem for a noble gas. So if we go to the periodic table, we're talking either helium, neon, argon, krypton, xenon, radon. All right. So if we go to the JANF, the NIST JANF thermochemical tables, we'll look up, for example, let's say helium. Okay. So the specific heat capacity at constant pressure is constant from 100 to 6,000 Kelvin. Okay. So that is what I mean by a perfect gas. So the noble gases, they are all monatomic perfect gases. Okay. So the heat capacities at constant pressure and at constant volume are both constants. They do not depend on the temperature. Right. All right. I'm going to set it up so that you could choose any one of those noble gases. How many are there? There are 1, 2, 3, 4, 5, 6. I'm gonna leave this one out. Okay. Um, so we're gonna set this up for those 6. Actually, I think even hydrogen would work. Let's see if we go back to Janif. Okay. Hydrogen gas. Okay. 20.786. All right. So this also worked for hydrogen. Okay. All right. You know what? We'll keep that for the end. All right. We'll just do this for AR, for argon. Okay. Okay. So I'm just gonna bring in code. Future videos will go over the theory of the different parts of the code that I'm gonna go over today. Okay. Um, Other videos might include deriving, some of these. So for example, the basis functions in 1D and 2D, the phase space Fourier transform. Okay, so I'll make separate videos on those topics. The first video is really just to show you the potential of the methodology for these types of problems. Okay, So NT, that's going to be my number of time steps, which for now, we'll just set that to 1. NNV is the number of velocities, the number of quantized velocities. I'm going to set that to 9 for now. NNX is the number of nodes in space. We'll set that to 20 for now. Okay. The length of the domain, we'll set that equal to 2. MNV is the middle velocity node number. That's where our moments or observables or expectation values are going to live. So it's important that we know what that position number is. DX is our grid spacing. All right, so let's save this and run it. So NT is 1, all right, and then X is 20, and then B is 9. Our middle velocity node number is 5 because NNV is 9. DX for now is 0.1. All right. So now let's generate our spatial nodes. We're going to generate a uniform grid. However, we're going to set the code up for a non-uniform grid because future videos will include non-uniform grids once we get through how to set up the code for 1D and 2D uniform grids. Okay, so our spatial grid, all right, it's just spaced out by dx, which is about 0.1, all right, from 0 to 2. Okay, so it's a very simple for loop. There's multiple ways you could do that using MatLab, all right. We're going to create a stepping vector in a similar manner. So there's my stepping vector when I have 9 velocity nodes. All right. The MNV will reproduce 0. So if I go step at MNV, that is 0. All right. I'll explain more on the step vector as we go forwards. Okay. There's just a couple basic data structures that we want to set up. All right. What I'll bring in next is my wave function matrix. It's my Fourier transformation function. So I just wrote a paper over the summer. It's called a precursor to the quantized velocity finite element method. All right. So we skip through the classical mechanics. We'll skip through the thermodynamics. And we'll go to the quantum mechanics section. All right. So here's my Fourier transform of my, so we'll be using a velocity distribution. In this paper, I'm using a momentum distribution. This psi is what we're generating right now in the code. So I have a vector of p's, or I really have a vector of v's or xi's. I have a vector of chi's, and the chi's I denote. So the chi's represent the virtual displacements. All right. So we're going to generate psi. Okay. So there is psi. All right, it's going to be 2 pi I, where I is the imaginary number. Okay, step A, step B, oops, divided by NNV. Okay, so these details can be found in that paper. All right. So within this very same section, I go over the quantization procedure. So Z alpha is our stepping vector or our step vector, equation 76. Okay, what we just put in the code is equation 78. All right. Equation 79 is the discrete Fourier transform and the inverse operation. Okay. All right. PSC is the complex conjugate wave function. All right. So the only difference is, right, this goes from a plus to a minus. Okay. We're next going to go to the NIST website and we're going to go grab some universal constants. We're going to go get the Boltzmann constant. We need the Planck constant. We're going to go and get the Dalton unit as well. Okay. For example, we'll go Boltzmann constant, NIST. Okay, so I just copied and pasted this value. So the Boltzmann constant, the Planck constant. Oops. All right. So I'm putting in H bar, so it's this number divided by 2 pi and the Dalton. Okay. All right. So we'll go back to the periodic table. So for argon, okay, we have a mass of 39.948. So I rounded that. That's based on the NIST periodic table. All right, so that 39.95, that's where I'm getting that from. Okay. All right. So next, what we'll do is define the specific gas constant, which will be the Boltzmann constant divided by the mass in kilograms. So this is the mass in kilograms. HS is the specific reduced Planck constant. Okay. So this H is HS in the code. This is HB. This is mass in kilograms. All right. We are going to work in kilograms, meters, seconds, Kelvin. So if we go on to the JANF website, we take that CP value and we divide it by the molar mass, we will have the specific heat coefficient at constant pressure. Okay, then we can use the Meyer relation to get the specific heat coefficient at constant volume. So this is a monatomic perfect gas. So our specific heat coefficient at constant volume will then be 3/2 times RS. Okay. There's my CV. All right. So we'll next initialize the density, velocity, and temperature. They all have spatial dependence as well as time dependence. So these quantities are going to evolve in time. We're going to simulate the sod shock tube. Okay. So the density in the left region will be 1 kilogram per meter cubed. The density in the right will be 1/8. The pressure in the left region will be 10 to the 5th pascals. The pressure in the right region will be 10 to the 4th pascals. Okay, so I'm going to now assign my initial observables, and the velocity is just going to be 0. Okay, so this is going to assign half the grid to the left quantities and then the other half of the grid to the right quantities. So NNX here should really be an even number. Okay. NNV should always be odd. This for this particular problem, because we're splitting it into a left and a right, if we want the same number of nodes in the left and right, that should then be an even number. We are now going to begin time marching. So we'll initialize the time, set that equal to 0, and then we'll do for t equals 1 to nt. Let's also close out the loop, all right? So the first thing we have to do is we have to determine our zone of influence. So we have velocity distributions. All right. So let's go into, you go into my dissertation. There. For example, we have a velocity distribution. This is on page 48. Right. So this is a continuous distribution. I go over the quantization procedure in both my dissertation and the paper I just wrote over the summer. We are going to quantize it. All right. So every quantized velocity represents a sample point. So we are going to sample the flow. All right. So we need to determine the limits of our sample points, the minimum and the maximum. Once we have our min and max, we'll then fill it in with sample points. So the important thing here is that we capture all of the important information. Okay, so the velocity distribution function that we're using is the Maxwellian, which is a Gaussian. So this stuff over here, well, at least this right here, right, the square root of the specific gas constant times the temperature, that is the standard deviation. I'm going to use 4 standard deviations. So if you go into, so we stick with my dissertation, all right? The quantization procedure is in section 3.8. Okay. Here's your step vector. This is your characteristic speed, which we are going to determine. All right, so we're going to put 229 into the code. If you go into the precursor, we're going to go back into that quantum mechanics section. Okay. So essentially we are putting in line 77, but this is momentum. This is the characteristic momentum. So you divide by the mass, okay, and then we don't need to worry about momentum anymore. So this is translational momentum for a particle. So m times v, divide by m, now we're working in velocity. So we won't be working in momentum, we'll be working in velocities. So in some sense, you could say we're using the Lagrangian formalism. Okay. So we're going to take the absolute value of the velocity at every spatial node. We'll add 4 times the square root of RT. All right. And we're going to go and find the absolute maximum. So I'm just going through and I'm testing. Okay. Or you could just define this as a vector and use MATLAB's built-in maximum function, and it'll give you the maximum. Okay. Let's now go ahead and compute the characteristic speed. Okay, so we are now computing equation 229 in my dissertation, which corresponds to 77 in the precursor. Okay. We are now going to initialize we're going to compute our quantized velocity lattice. So that's going to be the step vector times the characteristic speed. So this will update at every time step, but our first characteristic speed will be 316 meters per second. And then what we'll do is, okay, let's spit out xi. All right. So these are our quantized velocities. We're going to add more, but we'll do that at the very end. Okay. Associated to the set of quantized velocities are the set of quantized virtual displacements, which I denote chi in both my dissertation and the precursor. So chi will be 2 pi h specific divided by the number of velocity nodes times the characteristic speed times that step vector. Okay. So let's see, this is your chi. So after you plug in the formula for this wavelength lambda, so lambda is 2 pi h bar divided by delta p. So for us, it'll be lambda is 2 pi h specific divided by delta xi, or this c here. Okay. Or you could just, go into my dissertation. Okay. So here's lambda. All right. Here's delta chi, and then here's chi. All right. So all the details are found in both of these papers. Okay. So pi will be small because we're multiplying it by h specific, which for argon is this. So the units for H specific is meters squared per second. Okay, so our chi's, oh, let me run the code. Our chi's are, so they are on the order of a angstrom. Okay, times 10 to the minus 10. So they're small. All right. Let's now compute our time step size. So my dissertation, we're going to go to equation 230 and we're going to put that in. So if you have a non-uniform grid, you have to use the absolute minimum step size, whether it's an X, Y, or Z. Okay, because if you don't, what's going to happen is the information is going to travel outside of the domain of a space-time element. And then what you have is your computation is no longer physically meaningful, right? If it leaves the domain, it doesn't, it doesn't mean anything anymore. Okay. So this is really, really important, right? If you want your code to be stable and spit out results that are physically meaningful, equation 230 is a must. Okay. So the time step size is not arbitrary and it's going to change. So every time step, your delta t is going to change. So delta t is in a sense, it's going to be a function of time itself. Okay. And then I would like to compute the time because I would like to know, okay, what time is the simulation at? So I will add dt to the time. So the time we initialized at the very beginning here before we started time marching, right? Okay, so let's look at that really quick. So as your grid size goes down, so will your time step size. Um, So I set this up to end at a particular time. Um, we don't really need to go through that though. I like to also spit out this I will put in because I like to know where the code is at. All right. So, right, this is advanced one. Here's your DT for time step one, and then here's your total time. Okay, so for example, we have two time steps. All right. So that's a personal choice. I like to see where the code's at. All right. What we'll do next is so you could look at this, right? So we're gonna basically follow 231. We have to put in our moment generating wave functions. Okay. So we're going to put in, actually, I should use my dissertation for this. We're going to put in the quantized form of equation 213, which is the moment generating wave function. So using this Fourier transform, the velocity distribution, it's a function of xi. We take the Fourier transform. It is now a function of chi. It is now a type of moment generating function. So it stores the moments. All right. So there's a particular nodal value where our moment slash moments will be located. okay, and they are located at MNV. Let me initialize that from the very beginning. Okay. So we have to put in psi, or 213. So if you look at 213, when there is no mean velocity v, it's actually a Gaussian. Okay, but when there is a mean velocity, then we have the imaginary number, and then this becomes a complex valued wave function. All right. So I'm going to call my moment generating wave function capital G and my velocity distribution capital F. We're going to evolve, right? So we have a velocity distribution for the mass density, a velocity distribution for the momentum density, and a velocity distribution for the total energy density. So we're going to have 3 velocity distributions in this 1D code. Storage is important. Okay, so when you get to higher dimensions, you have to store, right? We still have to store all these quantities, so you might run out of storage. So instead of storing all 3 in 3 separate data structures, I'm only going to store 1 and I'm going to loop. So I'll do rounds. So I'll say, okay, round 1, G will be set equal to 213. Round 2, G will be set equal to so it'll be set equal to 223. Yeah, G will be set equal to 223. So round 1, we'll set G equal to 213. Round 2, we'll set G equal to 223. Round 3, we'll set G equal to 224. Okay. So I'm just gonna bring all this in and I'll talk about the code. So for round equals 1 to 3, we're going to begin our rounds. G is going to be zeros, and then X comma NNV. So this is your quote unquote phase space. All right. And we have to loop through space and through the velocities. So when I loop through space, I like to use, IJK. When I loop through the velocities, I like to use like alpha beta. So in the code, I'll use A and B. This is thermodynamic beta. This is your thermal frequency. I call this thermodynamic omega. This is your virtual potential energy. I discuss this in the precursor. Okay, and this is our moment generating wave function, which was 213. So round 1 set G equal to the moment generating function. Round 2, set it equal to the moment generating wave function times. So this stuff is this stuff. Okay, now for the energy, this stuff is this stuff. All right. And our total energy is 1/2 E squared plus CVT. Okay, so this is only applicable for the perfect gas model when our internal energy is equal to CVT. We'll then initialize F0. So F0 will be the velocity distribution at T. F1 will be the velocity distribution at T plus delta T. So in order to get the initial velocity distribution, okay, we have to extract it from G. So in both papers, I refer to the discrete Fourier transform going from the velocity distribution to the moment generating function. Okay, so we're going from the moment generating function to the velocity distribution. So this is technically so if you go online or you look in the literature, these terms can be used, right? You can call, right? I can call this either the discrete inverse Fourier transform, or I can call it a discrete Fourier transform, as long as I call the opposite transform the opposite of what I called it. Okay. So so this will be my discrete inverse Fourier transform. Okay. This is our complex conjugate wave function, which is a matrix. All right. You then dot it with the vector of g's divided by nnv times cs, which cs is the characteristic speed. So let's look at that computation. Okay. So in the precursor, line 79, we're computing our F alphas here. So here's the complex conjugate. All right. So this is in 3 dimensions. We're only in 1 dimension. So instead of n cubed, it's really n to the first. Same thing here. We'll get rid of that 3, replace it with the 1. If you're in 2 dimensions, then the 3 gets replaced with a 2. Okay, so this is what we are doing here. Okay. All right. So now that we have our initial distribution, let's take this stuff out for now. So I actually want to show that computation. All right, so row 1 is node 1 in space. Row 2 is node 2 in space, okay? All the way up until the last node in space. So each column represents a quantized velocity, okay? So those are our occupational velocities. So for example, all right, F0, so this actually probably looped through each round. Yes, this looped through each round. So that would be the energy. So let's actually do this just temporarily. I'll set round equal to 1. They're very small. All right, so we get some small negative quantity. As we add more velocities, shouldn't have any more negatives. About 13. We'll use 21 for the sod shock tube. Okay. It might just be easier to look at the total energy. All right, so we're using 13 velocities. I don't have any more negatives. Okay. All right, because mass cannot be negative. All right, mass cannot be negative. So let's actually look at the energy. We have negative mass, then our output physically doesn't mean anything. So this is the total energy density velocity distribution. That's bit of a mouthful, but okay, so this is our middle node. All right, so it should peak, right? It's a Gaussian. It should peak here. Okay. Then it should be symmetric because there is no velocity right now, so it should be symmetric on the left and right side. Okay, then we're going 51, 7 point. All right, so this looks good. This looks good. For example, something that doesn't look good. So since I'm using 4 standard deviations in the precursor, I go through this. We have 4 standard deviations, then our minimum number of velocity nodes has to be 9. If we're going to use 3 standard deviations, then the minimum number of velocity nodes is 7. I've had more luck when I use 4 standard deviations. Really, the more velocities, the better. Now it means that, our code is going to take longer to run, but the more velocities you use, the better results we're going to get. All right. So I use 7 here. So 7 with 3 with not so we're going to use 7 velocities, 3 standard deviations. Okay, I'm going to show you what it gives. All right, now we have negatives, right? The total energy, 1/2 V squared plus CVT, that will not be negative, right? So this is what I mean, right? Our scheme blows up, okay? So we have to use 9. And those details, again, are in the precursor. 9 when we use 4 standard deviations. In the precursor, that is discussed at the end of, here it is, okay? So this is the stability condition, but then for accuracy, wait, no, hold on. This is the stability condition, 81. For accuracy, that's the accuracy condition, 82. Okay. This n is the number of standard deviations. This n is the number of velocities / virtual displacements. Essentially, it's the size of our lattice, of our integer lattice vector, which is symmetric. I like to run my code as I run it so that I make sure that it's doing what I want it to do. Okay. So again, this is the total energy density velocity distribution. There's going to be some very small imaginary part right now. So the initial velocity is 0. We only have a small imaginary part because we are using MATLAB, right? We're using a computer, so we have to store numbers. The numbers are only stored up into a certain decimal place. Okay. Imaginary part of 0. Okay, so for example, right, these are very small. So those are numerical artifacts because we're using a computer and we're storing the numbers up into a certain decimal place. Okay. So really 92, really before this actually. So from 70 to 116, okay, that's the quantized velocity part. Now we're going to put in our finite element solutions over the space-time elements. In this next paper I'm writing, which is going to be the first real official quantized velocity finite element method paper, I am going to not necessarily redefine what I call this phase time element, but I'm gonna just tweak the definition of the phase time element as a collection of space-time elements. It'll also make more sense in comparison with the Boltzmann collision integral. Okay, so those details are will be provided in the next paper. All right. Um, but essentially what happens is we have a collection of space-time elements. Okay. Those details can be found in my dissertation. Okay. So really, I think I'm going to redefine. Yeah, so this is going to be a space-time element. Essentially, this whole thing will be I'm going to call that a phase-time element, and it's going to be a collection of space-time elements, and the arrows are going to be reversed. It's all going to be going into a single node here. All right. But these details can be found in my dissertation. This is section 3.4. We will not be including viscous effects nor thermal conductivity. So the process will be isentropic, meaning there will be no entropy production. So the entropy is technically also a conserved quantity when we're solving the Euler equations. Okay. So really, here's our space-time element. All right. We have, let's say here's node I plus one in space. All right. So time is going from node 2 to node 3. Okay. So in order to move through space, you have to move through time. Okay. So again, we're sampling the flow field. All right. There's a flow. Okay. So the solution represents, right? The solution is essentially this guy here. Okay. So we have it could be some amount of mass, it could be some amount of momentum, it could be some amount of energy, it could also even be some amount of entropy, even though we're not going to put the entropy in the code. Okay. So that amount is at node 1 at Tn. And then as time marches forwards, okay, that information is going to travel from 1 to 2 with velocity xi. Right? So imagine a flow field. Okay, it's flowing through node 2. You know, you can even think of this as a finite volume as well. There's finite elements, but within the elements are also finite volumes. Okay. So the solution at node 2 is this guy here. Okay. Right. So let's go and compute. We're going to compute this guy in red. Okay. That's what we're now computing. All right. Okay. So I will talk about these shortly, but let's just comment that out for now. You know, I'll leave this. That's fine. Okay. So we're going to loop through space, loop through the velocities. And this And X naught is this phi inverse. Okay, so there's a bit of continuum mechanics here. Okay, if you're interested, actually, if you're writing this code, you really should look at the continuum mechanics from how the equation of motion is derived, which is the free stream Boltzmann equation, but from a continuum mechanics perspective to finding the solution. Okay, so we are essentially time marching um, analytical solutions. I know that's kind of a bizarre concept, but um, when you rewrite the Euler equations in terms of velocity distributions, the equations of motion simplify greatly. We can find analytical solutions. Okay. So we have the analytical solution over each element. We just have to put the solution in. All right. Where do I give? Here. Okay, so 143. This is what we're putting in, this x naught, which is phi inverse, okay? That x minus xi t. This is the motion. Okay, so 143, right-hand side, that is line 128. Okay, so depending on the velocity, so really the velocity dictates the size of the element. Okay, so x1 will be xx at I minus step A, and then x2 will be xxi. All right, so all these space-time elements are different sizes. Okay, and they all overlap each other. Um, what we're doing here is we're using the principle of superposition and we're solving multiple equations of motion. You look at 139 and 140. 139 is the continuous form. 140 is the quantized form. That's what we're solving. And they're all independent, right? I could set this first equation of motion equal to 0, the second one equal to 0, the third one equal to 0. So then when I sum all the individuals, the total is also equal to 0, right? Um, that is a pretty standard way of doing things when it comes to, let's say, for example, solving the heat equation where your mass density, heat capacity, and your coefficient of thermal conductivity, right? Let's say if these things are constant, okay, you can then solve that equation using a Fourier series, all right? This is very close to that. Actually, in the next paper, I'm going to go over how to put in viscosity and thermal conductivity. We will be using a specialized Fourier series interpolation of the element. So it will actually become a Fourier series at some point. But when we don't need to worry about, or at least when we neglect viscosity and thermal conductivity, we can use a standard finite element interpolation. Okay, so all you have to do is interpolate the element in space, and then your space-time solution, you set x equal to x naught. Okay, so for example, where do I go over here? Okay, so when you set x naught equal to x minus xi t, that's your space-time solution. Okay, so that gives you the motion over the element. Okay. So here's our domain for each element. Okay. BF is basis function, so we're only a 1D. So we are dealing with only line elements. So we have a straight line, which is connected by 2 points. Therefore, we only need 2 basis functions, right? So our solution is written as so, right? It's our nodal values. It's a vector of nodal values dotted with our basis functions, which here I'm using G. Sometimes people use psi. I'm using psi for the actual wave function or even capital N, which it just doesn't go with my notation, okay? So I'm using G. Okay. So here's our basis functions. Okay. Our FF is our nodal values, which we go and grab those from F0. So what you can do is you take X1 and X2, copy and paste it, place that with, right, FF1, FF2, okay, and then this will be F0. Right. And then I will sum. Okay, so I'm going to say, okay, F1 equals F1 because I initialized F1 as matrix is 0. So F1 equals F1 plus FFK times BFK. So your each nodal value times the basis function, right? So here's our F1. This is what we just computed. Okay. So when the velocity is 0, if we go to our equation of motion, when our velocity is 0, the temporal change in F is equal to 0. So nothing happens. So at those middle nodes, we're going to assign F1, right? When the step number is equal to 0, F1 equals F0. Okay, so we just filled in the middle column. Oh, whoops. All right, so again, we just filled in the middle column. All right. So again, right, this is node 1. This is node 2. This is node, so these are our final nodes down here. So at the beginning and at the end, we're near the boundary or we are on the boundary. Okay, so depending on what the velocity is, whether it's positive or negative, the information stops at the boundaries. So it doesn't make sense for information to be, right? Information is not going to go through the boundary wall. It's also not going to come from the wall because the wall's where the boundary ends. Okay, so the most simplest form of boundary conditions is to simply set these values here equal to F0. All right. So for example, right, if there's no information coming, right, traveling, or I should really say, right, if the information cannot go through the boundary walls, it's just going to stay there, right? Nothing's going to happen. Okay. So I'm going to set near the boundaries these quantities here equal to F0. So F1 will equal F0 here. Okay. So if this was the Lattice-Boltzmann method, maybe you would implement some type of like, bounce back or, I haven't really looked into scattering kernels at this current point in time. That'll be, so I'll look into some boundary conditions in the next paper. But for now, the simplest method is to simply set F1 equal to F0 at those values. Okay. All right, so if I minus step A is less than 1, okay, F1 equals F0. If I minus step A is greater than NNX, again, F1 equals F0. All right, so there's our solution for the first time step. At least for the total energy density velocity distribution. All right. What we'll do next, um, what we'll do next is let's go to my dissertation and we're going to follow the steps here. So from our initial G, we have F0. We applied our equation of motion, or we applied our solution to the governing equation of motion. We now have F1. We're now going to take the discrete Fourier transform, and we will then generate essentially G1. So this is G0, this is G1. I'm just going to override G. Okay, so that's what I'm doing here. So this last part on the right-hand side of 231, that's what I'm doing here. Right? So that's psi. This is a matrix, dotted with the vector of F1s, and times the characteristic speed. Okay. So instead of momentum, I have velocity. Okay. So we're still within that round loop. So I can't necessarily, yeah, I cannot update the observables just yet. I'm gonna have to store them, and I'll store them within M0, M1, M2, standing for moment 0, moment 1, moment 2. Okay, so at that middle velocity no number, that's where my updated moments exist. Okay, so I get my updated 0th order moment, first order, second order. Okay, so this represents the updated mass density, updated momentum density, updated total energy density. All If I do, let's real part of G. All right, here's my updated moments in this middle column. Everything else is virtual, whatever that means. Okay. If if the quantum mechanics scares you, right, you can really set H bar equal to 1 for now. Maybe some of the observables will start changing in the virtual space. Maybe that's a way of handling thermal non-equilibrium over the time step. I don't know. I don't know yet. I really don't know. That's something to be investigated. But there is, so with the precursor, um, that was an appropriate space to investigate some of the quantum mechanical aspects of the Fourier train. Is it just, math, or is there really something to it? And if you go through here, okay, you go into the section on the thermal de Broglie wavelength and the Sackur-Tetrode equation. So there are thermodynamic consequences of the Fourier transform. So here I'm exploring the limits of the model and the limits of this type of Fourier transform, when we're using the Planck constant. Okay, is there a minimum spatial scale? Okay, is it related to the entropy? Okay, yes. All right, so I'm gonna let you guys, you know, read that. I might make some separate videos going through the theory without any MATLAB. All right. Um, if there's any requests, let me know. I guess you would leave that in the comments. I'm kind of new to this YouTube thing. All right. So we're done with the rounds. We now have our M0, M1, M2. So it's time to update the observables. Okay, the density, velocity, and the temperature. All right. So the new density is M0. Right, I can't assign this to the density because it's going to go back up, right, after round one. Okay, then round two, right? Um, hmm. Maybe I could update the density because I don't see density in here, but the velocity, right? We can't update the velocity. You still have to use the original velocity. Same thing with the energy, right? Well, actually, I'm updating, right, the moment generating wave function here. So yeah, I can't update the density. Okay, so that's why I'm storing them in M0, M1, M2. Then once we're done with the rounds, now, okay, the updated density at T plus delta T is M0. The velocity is going to be M1 divided by M0. All right, and then M2 is the updated total energy density. So I have to subtract out the kinetic. Okay, so this is the total minus the kinetic. All right, this is the updated internal divided by CV because we are using the perfect gas model. That is the updated temperature. All right. I'm going to run this code and then I'm going to save the output. All right. I'm also going to get rid of a bunch of variables that I don't want in there. All right. I'm going to go back to the top of the code here. I'm going to set NT to, let's say, 500. I'm going to set my NNX. We'll use 5,000 nodes. I'm going to use 21 velocities. You know what? Let's set an end time. Maybe I want to run it till 1.2 milliseconds. So if we go over that time, we'll put a break statement in to exit the time loop. Okay. And we're gonna run it. So this is the exciting part. long as your code works. All right. So let's see. What can I talk about while it runs? Or we could just wait. Let's talk about the elements. We'll talk about the elements. Okay, for a uniform grid, this really breaks down to method of characteristics, where there's multiple characteristics coming out of every spatial node. Okay, right. So again, we're dealing with a velocity distribution, right? So this is a distribution of occupational states, right? How much mass, momentum, and energy is occupying a certain velocity. Okay. So what we're looking for is, all right, how do the number of, let's say, particles or atoms or molecules, right? How do those numbers within each within each occupational velocity change over time, right? So the velocities over the time step don't change. Those are all quantized. And the number of particles occupying those velocities, that's what is going to change. Okay. Here's that omega, so I'm just calling that thermodynamic omega in the precursor. If you read the precursor, the first section with the classical mechanics, okay, just this L doesn't need to be a function of time. So the precursor is built around the assumption of the total energy of the system being a conserved quantity. So L is not going to have explicit dependence upon time. Okay. So that theoretical derivation um, corrects the attempt here. So it's the same results, but this how I did this is not necessarily accurate. Okay, because actually you can't put so this term you can't put in here. Yeah, but I fixed that in the precursor. Okay, let's go talk about the elements here. So this is an example in 2D on the right, example in 3D on the left. So at every spatial node, right, there's going to be some dispersion. All right, again, there's some amount of mass, momentum, and energy occupying each quantized velocity state at every single node. So when we begin the time step, right, we're going to then transport all of that information, okay, according to the occupational velocity. And that information, right, is going to disperse over the spatial grid, as you can see on the right here. Okay. So this would be an example of a 2D element. So when we're in 2D, we would have line elements and quadrilateral elements. Okay. In 3D, we'd have 1D, 2D, and 3D elements. Okay, within a single phase time element. All right. All right. Getting there. Another thing that I am currently investigating is setting the code up for parallel computing. So whatever the Lattice-Boltzmann method does, it's essentially going to be the same as far as parallelizing the code, to break up the computations and run multiple parts on multiple CPUs at once. Okay, so I just got access to um, a more powerful computer, and I'm setting up the code now. If there's any suggestions on what language to use, um, I'm either going to do it in C, C++, or this language called Zig. I'm going to avoid Fortran. I just don't like writing in Fortran. I don't like declaring all my variables at the very top. I don't like Fortran. Um, so there's this language called Zig. That's pretty new. I want to give it a go. I've actually already written the 1D code in Zig on my own personal computer, but I got to set up. I have to download the compiler onto this new computer that I just got access to. So once this thing is done running, you're going to see how stable the code is. A major benefit is that if the code isn't stable, all you have to do is change a couple numbers. What are those numbers? Go to the top, your phase space numbers, all right? Your number of velocities and your number of spatial nodes. Okay, if it's not working out, we're not using enough velocities. Okay, so you have to add more information to get a stable solution. Um, so for example, right, let's say you're using a we know, eno, tino type of method, right, where you have stencils. Okay, now these elements are analogous to those stencils. You would then have to so let's say if you want to increase your stencil size, you now have to go rederive your your scheme and then put those equations back into the code. All you have to do is change a number. Okay. Same thing with the quantization of the velocity space. Um, a lot of current methodologies, you would have to really, if you want to increase the number of velocities, you have to go back to the drawing board. With the method I have proposed, you just change the number. All right. So this is a general algorithm that we're setting up. If the grid was non-uniform, this code will work as well. Okay, so we could have actually used the streaming algorithm from the Lattice-Boltzmann method in this because our grid is uniform instead of using basis functions. But once our DX starts having spatial dependence, that's when I need my basis functions now. Okay, so again, the goal is to set up a general algorithm so that you could just, adjust the initial conditions, adjust the geometry, and then run it. Okay. The end goal is to have this be used for some type of commercial use, maybe by the United States military. Okay. Right. This thing, this thing actually burnt. Um, okay. All right. So it's done running. So on the x-axis is space. Y-axis is the density. Here's our shock wave over here, and it's actually moving with a constant velocity, okay, from the left to the right. Here's your expansion fan. All right, so let's go ahead and let's zoom in. Let's see if there's any small oscillations in this code. Okay, so because we're inputting analytical solutions, the output is of analytical quality. Um, there are no oscillations here. You know, it's a pretty good feeling because right, for anyone who's written CFD code, um, this can really be a bit of a headache trying to get stable solutions. So um, it's really nice when you see stuff like this. Like that's, oof, look at that. You know, I mean, and this method is also verified in my dissertation. I verify it using two methods, one from the analytical method, and then another from looking at the shock wave speed, because it's actually a constant, as I previously said. So if you go into those benchmark problems, my dissertation in section 3.9, okay, um, this is me verifying the speed of the shock wave, okay, and then there's a code on the MatLab website by Virginia Notaro, right? That's how I generated this magenta solution. Okay, so that's like your analytical solution, right? So there's the density. I want to show you guys the velocity actually, because I don't know if I really agree with the analytical solution. So there's a spike in the velocity at the very. I don't know if you notice at the very beginning, right? But there's going to be a spike in the velocity. Okay, and it takes time for that velocity to relax. Where in the analytical solution, it's just kind of instantaneous, where it's just a straight shot. Now, when I say relax, all right, meaning this bump is going to get smaller as time marches forwards. Okay, so I actually trust this more. Now, look at this jump in the velocity. Let's just zoom in here. Let's see if there's any squiggles. Nope, right? Perfectly smooth, perfectly smooth. Um, Here's the velocity. Typically, I show the momentum density. So that's going to be the density dot times the velocity, right? Right. So our density that's mass density. So that's kilogram per meter cubed. So that times the velocity, that's going to give us our momentum density, all right? Really nice looking solution here. Uh, Without trying to toot my own horn, but all right. And again, right, the same code can be used for the lax problem, the double blast wave problem, but these problems require more nodes, right? But they need more information. I think for the double blast wave problem, I use 30,000 spatial nodes and 251 velocity nodes. So in this Shock 2 problem, I'm using, so in comparison, I'm using 5,000 spatial nodes and 21 velocity. So this one took a lot longer to run. All right, let's look at the temperature. Oh, okay. All right. So everything's checking out. Right? There's no oscillations, even as I zoom in, right? There's no little squiggles. It is actually straight. And look at the pressure. So I didn't save the pressure, so let's do this. We'll do pressure. It's going to be the density dot times the specific gas constant dot times rho RT, the temperature. Okay, here's the pressure, and I'm going to go scatter. Okay. Here's the shock wave. All right. Everything checks out. Really smooth. Okay. So, if you did watch this video, thanks for checking out my first one. The next one, I'm thinking we'll extend the perfect gas model into the ideal gas model. Maybe we'll simulate like N2 or O2. We'll incorporate the rotational and vibrational energies, and we'll compare the perfect model to the ideal model, where the specific heat coefficients will now become dependent upon the temperature. All right. So I hope you enjoyed this video. Hope you can actually replicate what I do here. Thanks for checking it out, and I'll see you next time.